In this video, we look at the binomial theorem. In order to understand why and when we might use the binomial theorem, let's first look at expanding a plus b squared. Remember that a plus b squared really means a plus b times a plus b. So we can go ahead and use the distributive property, multiply everything in that first set of brackets by everything in the second set of brackets, and in the end, we'd come out with a squared plus 2ab plus b squared. We won't actually do the expansion, but if you wanted to, you could double check. Let's move on now to something a little bit harder. A plus b cubed, same idea, is a plus b times a plus b times a plus b. So what this means, we're going to take everything in this first set of brackets here and multiply it by everything in this set of brackets, second set of brackets, and then we'll take the result and multiply by everything in this set of brackets. Now I said that this was harder. It's not necessarily harder, it's just much more time consuming. Again, I'll save you the time here and spare you the details, but in the end we'll get an a cubed plus 3a squared b plus 3ab squareds plus b cubed. And things get even longer if we're looking at doing a plus b to the fourth. So a plus b to the fourth, we would do the exact same thing, and the final result would look something like this: a to the 4 plus 4a cubed b plus 6a squared b squared plus 4a b cubed plus b to the 4. So this is a very long process, as I mentioned, and what the binomial theorem does for us is it allows us to save a little bit of time. It gives us a shortcut for doing these types of expansions. So it's called the binomial theorem because each of these here are binomials, and we're expanding these binomials. Now, one thing that hopefully you'll notice here is if we look at the coefficients of each of the terms here, there's an understood 1 here, a 2 here, and a 1 here. A 1, a 3, a 3, and a 1. A 1, 4, 6, 4, and 1. These numbers come from Pascal's triangle. So Pascal's triangle, reminder, looks sort of like this. We just add each number sort of directly above or adjacent and above to each number. So 1 and 1 gives us 2. There's an understood 0 here, and we continue this pattern, and you'll see that the numbers here in the triangle correspond to the coefficients of the expansion. And that's true when we do these expansions, and that's going to save us a whole bunch of time, because instead of doing the expansion, what we can do is we can actually jump right to this line, say in Pascal's triangle, and say, hey, these have to be the coefficients over here, and then we just have to figure out what's going on with the a's and the b's. So a couple things that you should notice here. We'll talk a little bit more in detail. We'll do an example shortly, but a couple things that you should notice here is that for a plus b to the n, the coefficients come from Pascal's triangle. We talked about that earlier. The other thing that you should notice, let me just flip back here, is that the exponents on a, let's go right to the top here. The exponent on a here started as a 2, then it went to a 1, and then it went to a 0. This is the same as a to the 0 times b. Remember that a to the 0 is just 1. So the exponent here started as a 2, down here it started as a 3, and down here it started as a 4. Well, notice that those numbers are the same as the exponents on the binomial itself. So the exponents on the a's started at this value right here, and they decreased by 1 every time. So it started here as a 2, then went to a 1. Here it started as a 3. Let's try that again. A 3, a 2, and then a 1, and then a 0, and so on. And then look at the exponents on the b's. So just a reminder, maybe we can jot this in here. This is like having a b to the 0 in here. B to the 0 is 1. We generally don't write it in, but that's what it would mean. So again, if we look at the exponents on the b's, the exponent on the b was a 0 and then a 1 um, and then a 2. Sorry, there it is. And then same thing here. The exponent on the b was a 0, a 1, a 2, and a 3. So the exponents on the a's start at this value here and decrease by 1. The exponent on the b's start at 0 and increase by 1. So that's kind of what this bit says here. So the exponent for the a starts at n and decreases, that's important, decreases by 1 each time, and the exponents for b start at 0 and increase by 1 for each term in the expansion. And then the other thing to notice, maybe we'll just flip back at these examples that we did. You'll notice down here that the exponents on a and b, sorry, down here, the exponent here was 4. The total on the exponents here, there was a 3 and a 1 over here, a 2 and a 2, and a 1 and a 3 and a 4. The exponents always added up to give us this value here. So that's another important property here. So that's what this little last bit here says. The exponents on a and b add to n. So if we take those two exponents. Now, one of the things about this is that in order to do this, it looks like we have to draw out Pascal's triangle every time, which is a bit of a pain because that could take some time depending on what type of expansion we're doing. Here's another observation that you should make, is that the numbers in Pascal's triangle actually look a whole lot like this. 0, 2, 0. Well, that's just equal to 1. That's like the first row, row in Pascal's triangle. The next row would look like this. 1, choose 0, which is 1, and 1, choose 1, which is also 1. And then the next row would look like this. 2, choose 0, 2, choose 1, that's 2, and then finally 2, choose 2, which is also 1. I'll do one more here. Moving on to the next row would be 3, choose 0, 3, choose 1, 3, choose 2, and finally 3, choose 3. Sorry, some of these 3's are looking a little funny here. Try to fix that up. And that continues on. So the numbers in Pascal's triangle can actually be found just using this choose notation here. And so what the binomial theorem says, the sort of technical definition of the binomial theorem, is that if we have a binomial a plus b raised to the nth power, that's the same as doing n choose 0, because this, well, let's fix that up. This part right here we know has to come from Pascal's triangle, and that number corresponds to what we've drawn over here in Pascal's triangle. And we'll work through an example here so you can see that. The exponent on a starts at n, the exponent on b starts at 0, and then the exponent on a decreases by 1 each time, and the exponent by b increases by 1 every time. And here we're just moving from one element in the triangle, one column, I guess, in the triangle to the next column. So if we're looking at this third row here, we would start here for our first coefficient. Our second coefficient would come from here, our third from here, and so on. So that's what Pascal's triangle, how we can use Pascal's triangle to help us when we expand binomials. A short way to write this is this right here. So this notation is a little bit different probably for you. This funny looking symbol here is called a, let me just trace it out here for you. This is called a sigma. And it just means the sum of sigma. It means the sum of all of the n choose r's times a to the n minus r times b to the r, where r starts at 0 and goes all the way up to n. So we start r at 0, and I'm just going to write out the first little bit of this for you. So let's say we wanted to do down here we can do a plus b. We'll just keep it short here just so you can get an idea of the notation. A plus b squared. So in this case, the n is the exponent, so our exponent is 2. So everywhere in this equation where we see an n, we're going to replace it with a 2. And we're going to have an r, and r is going to start at 0. So really what this means is we're going to start r at 0. So our first little bit here says n. Well, n is 2, and we're starting r at 0. 2, choose 0. A to the n minus r. A to the n is 2, right? It comes from here. And r is this value right here, which is 0. And then we get b to the r, which is 0. So this was n, don't forget, and this is r. So we've done this now for r equals 0. What the summation notation means is that now just increase r by 1 and keep going until you get to n. So our next one will be 2 to the 1. So n stays as 2. So here's our n. And here's r. We did r equals 0, and now we're at r equals 1. So we're going to have a to the 2 minus 1, b to the 1. And now we've done our summation with r equaling 1, and we keep going until r is equal to n. So n is 2, r is now 2. So that's a bad 2. Let's fix that up. Let's really fix that up. So n is 2, r is 2. So we're doing 2, choose 2. A to the 2 minus 2. And b to the 2. And then we can evaluate from there and go ahead and simplify things. The point here was just to show you how this summation notation works. It's a shortcut that's designed to save you having to write all of this over and over again. So again, it's some new notation. It's notation that's useful because it does save a little bit of time. All right, let's look at an example. So let's expand 2x minus 1 cubed. Now we could write that as 2x minus 1 times 2x minus 1 times 2x minus 1. It's time consuming. So let's just walk through the binomial theorem to show you how that works. So we're starting with 2x minus 1 cubed. And it's probably worthwhile just pulling that binomial theorem in for us. Oh, not there. From the previous page. Let's see if we can kind of grab this and copy it over, just to keep you seeing what's going on. So paste that in here just as a reminder. So in our case, a is the first term, so a is going to be 2x in this case. So this is our a right in here, and this is our b. So things are going to get a little bit messy here, but that's okay. We can just work through it. So the first part here is to do n choose 0. Well, n is the exponent here, so this is our n. And we can do 3 choose 0. That's easy enough. 3 choose 0. And then we do a to the n. Don't forget a is this little bit right here. So we're going to do 2x to the n. Well, n was 3. And then we're going to do b to the 0. Let's try that again because we know what b is. B is negative 1. Just tidy that up a bit. This was a 2x with a 3. And we know that this is our b value. B is negative 1. So we're going to substitute a negative 1 in here to the 0. And then we're going to increase the value of r. So here's r, here's n up here. And we're going to decrease these. So these are going to go down. The exponents on a and the exponents on b. So these are going down. These are going up. All right, let's keep moving along here. So still n, choose 1 now. A was 2x. The exponent was a 3 before. Now it's going to be a 2. And b is negative 1. The exponent was a 0 over here. It's going to go up by 1. I'll write it in there. We don't technically need to, but we'll write it in there just to keep track. Then we're going to move on. 3 choose 2 times 2x. Decrease the exponent by 1. times negative 1 and increase the exponent on that negative 1 by 1. And as a quick check, just a reminder, you can quickly check the exponents here should add up to n. So n was 3. All of our exponents on the a's and the b's should add up over here. All right, let's keep moving along. We're just about done, I guess. 3, choose 3. Now n and r are the same, so this is our last one. We got a 2x to the 0. Subtract 1 from the exponent here. 1 minus 1 is 0. And then negative 1 here we're going to increase the exponent here. So once we get this far, we can simplify this. 3 choose 0 is just 1. 2x cubed, don't forget 2x cubed, maybe just on the side. Let's do it way over here. 2x cubed means 2x times 2x times 2x, which means multiply all of the 2's together 3 times, multiply all the x's together. So we're going to get an 8, x cubed here. And negative 1 to the 0 is just 1. Again, we don't need to put that in there. I think I'll just put it in there to show you. And same over here. We don't need to put 3 choose 0 as just 1 in here, but I'll just put it in there to show you where all those terms come from. So we'll simplify this again in the next line. If you prefer to leave those numbers out, you're more than welcome to do that if you have no trouble with that. So 3 choose 1 is just 3. 2x squared is the same as, 2x all squared is 4x squared. And then negative 1 to the 1 is going to be a negative 1. Again, we'll simplify that in the next line. Next up, 3 choose 2. That's just equal to 3. 2x to the 1 is 2x. And finally, negative 1 squared. That's the same as positive 1. And lastly, over here, 3 choose 3 is 1. 2x to the 0, also 1. And negative 1 to the 3 is going to be a negative 1. And now we can simplify all of this. So here we have a 1 times an 8x cubed times a 1. That's just 8x cubed. Here we have a 3 times a 4x squared times a negative 1. 3 times 4 is 12, times negative 1 is negative 12. And we have an x squared. Over here, 3 times 2 is 6, times 1 is still 6. And there's an x there as well. And then finally, 1 times negative 1 is negative 1. So we were able to expand 2x minus 1 cubed using the binomial theorem. All right, and so for the second part, or the last part of the question here, last little bit, it says, what is the 10th term in the expansion of 2x minus 1 to the 25? In order to do that, let's just have a quick peek here. Here the first term is here, so this was the first. Here was the second term. Here was the third term. Important to note that the term number is actually just 1 greater than the r value in each of these. So the r value being a 1 here and a 2 here, if we want to know what the 10th term is, so term 10, the r value should be 1 less than that. So for the 10th term, we should be doing n. So in this case, n is a little bit different here. N is 25. So in this case, we're going to do n, choose, not 10, we want the 10th term. We want 10, choose 9. And the reason for that is that this is the 0th term here. So the 0th term counting as a term. So it's counting as the first term, but that was a 0. So that kind of changes things a little bit. So we've got 25, choose 9. So without doing this whole expansion, we can tell what the 10th term is. It's going to be 25, choose 9. And then we take our a value. So again, this is a and this is b. 2x here. We know we're going to have some exponent here. Well, that exponent, let's come back to that exponent actually in a second. And then we know that the b value is negative 1. Notice here on our b value, the b value was always whatever the r value was. So the b was a 3 and a 3. Here it was a 2. We had a 2, and so on. Sorry, there's a 1 and a 1. So fairly easily, we know that this has to be a 9. And the other thing that we know is that the sum of the exponents here and here has to equal 25. So we should be able to do 25 minus 9 to get the exponent here. And again, we can kind of work this out on a calculator if we wanted to. I'm not going to bother just because 25 choose 9 is a really big number. But we could kind of go from there if we really wanted to. 25 minus 9 is going to give us 16. And then we're going to get a negative 1 to the 9 here. And again, we could simplify this if we wanted to, but I think for now, we'll just leave that as is. So that's a quick introduction, or maybe not so quick introduction, of what the binomial theorem is, where we use it, and how we use it.